Good morning. Welcome to episode 4 of AlgorithmsThread. Today we'll be talking about segment tree beats. Most of this is based off of a Codeforces blog post, and I'll link that in the description. If you're good at reading mathematical stuff, that might be worth checking out, and it's a good reference after you kind of know how it works to go through if you have questions and implementation details. For me, it was a pretty dense read, so it was a little hard to understand, so hopefully this should help out with that. So this is going to be about segment tree beats, and the main thing segment tree beats are good for is they can do this very special query. And the query that they're good for is rangeMinWith. So in particular, if you have some range of numbers, you can set each number to whichever is smaller, that number or like that number minus 5. Or sorry, that's not true. That number or like some integer x. And this is the very special query that segment tree beats are known for. You can also do rangeMaxWith, because it's pretty much the same as minWith, and you can take care of both of them at the same time. So before I go into segment tree beats details, I'd like to talk about this other segment tree problem, which is pretty interesting and uses similar concepts. So in this other problem, what you need to do is you have a bunch of queries, and each query is of one of two different forms. So the first form is you want to, for a certain range, you want to range mod each element by x. So each element you'll set to its value under mod of x, and then the second query you have to answer is rangeSum. So since we're doing these range operations on some array, it might make sense to use some sort of segment tree, and that's exactly what we're going to do. So we'll have some segment tree, and we can pretty easily handle the rangeSum if we can maintain what the sum within each node is, in the same way that we did in the previous AlgorithmsThread on segment trees. So if we know the sum within each node, we can easily maintain what this rangeSum is, and we can answer those queries pretty easily. The tricky part is if we have this range mod query, and maybe we have to answer some query that looks like this, then it's really tricky because for this node here, according to our normal segment tree logic, we would have to leave it in order 1. So we'd have to instantly be able to tell, okay, this entire node has been modified. We have to figure out how the sum will change in some predictable way. The issue is when you modify a bunch of numbers in some array, if you mod all of those numbers by a certain value, it's not obvious how the sum of those numbers will change. You need to pretty much look at each different element, or at least look at each different possible value of all of the numbers in that range, and it changes in like a weird way. So that's a very difficult thing to keep track of. So instead, what we can actually do is when we want to go into a given node, the first case is if none of the numbers will change, and that's easy to check. Because if the biggest number in our range is smaller than the mod, then none of them will be affected by the mod. But if at least one number does change, we can continue going to our two children. And you might think, well, hang on a second, if every time we're at some node that's entirely covered, we might go to all of your children, then in this big range, we might go to all of the nodes in between it. And if we do that, then the runtime of the segment tree will be linear instead of log n per query. And that's true. For a single query, then the runtime of the segment tree might be linear. In fact, for several queries, it might be linear. You might like have a bunch of numbers, and you might mod all of them by 10, and then mod them all by 4, and then by 2, and something like that. But the important thing to keep in mind is when you have some number, maybe you have like some number like 7, if you take 7 mod x, this number is always going to be less than or equal to 7 over 2, if x is less than 7. So if x is bigger than 7 and 7 doesn't change, then it'll just be 7. But if 7 does change, it will at least get divided by 2. And the important part about that is you can only get divided by 2 if you're an integer at most log times before you hit 1. And then you can't, like you can take it mod 1 and then it turns into 0, but then you're stuck. You can't do anything else. So the thing to keep in mind here is if we just do this solution, instead of it being n log squared, or instead of it being n squared, our runtime will be n times log squared. And that's a very reasonable runtime for the bounds for this problem. So cool, that's an interesting solution, I guess. The important takeaway here that goes to segment tree beats is that we don't necessarily have to break early. It's okay to visit our children in the array, as long as when we do visit our children, we're putting some guarantee on ourselves that this will simplify our array in some way that we won't be able to do this a bunch of times later on. In this case, when we visit our children, all of the values get closer to 0. And they get closer to 0 in a way that you can only get closer to 0 log times before you can't be visited anymore. So each node here can be visited at most log times. Segment tree beats are slightly different. The way the array gets simpler is a little bit more complicated. It's a little bit more difficult to describe than just things getting smaller, but it's the similar idea. All right, so let's move on to segment tree beats and how to handle this rangeMinWith query. So the main idea behind segment tree beats that makes them possible is for each node, we're going to store the maximum on that node, and we're also going to store the second biggest value. And when I say second biggest value, I don't just mean like if we sorted them, we'd keep track of the biggest and the second biggest. I mean like the second biggest unique value. So if the numbers inside some node are going to be like, I'll finish my segment tree here and then explain. So if the numbers are like 3, 3, 1, and 2, then when we get to this node here, its children are going to be this 3, the 3, the 1, and the 2. So what we're going to keep track of is we're going to keep track of our max is going to be equal to 3, and then our second max, like the second best, is going to be equal to 2. We're also going to keep track of how many of each of these we have. So we have 2 of these, 2 3s, and 1 2. Okay, so we can keep track of all of that for each node. That's a total of order 1 memory, pretty easy. And then what we can do is we can predict, because like what we need to maintain here, I guess let's write this down. So we need to maintain the max. That's an easy thing to maintain. We need to maintain the second max. That's not quite as easy, but it's just a bunch of casework. So if you have 2 children, the maximum is just the max of the 2 children. The second max, there are a couple different cases. Like you have to case out if the maxes of your 2 kids are the same, in which case it's the bigger of their second maxes, or if one max is bigger than the other max, then it's either the second max of the first or the max of the second, and stuff like that. So you have to case it out, but it's still pretty easy to maintain. We also need to maintain the sum. And the reason we need to maintain the sum is because we're answering these like rangeSum queries, right? So we need to be able to handle these. And that's really all that we need to maintain. So now the important thing is, if the value that we're minning this range with is between our max and our second max, then the only numbers that will change, I guess we need the counts of each of these too. So like, yeah, we need the counts of the max and the second max as well, but I won't draw those in. So if the value we're minning with is between the max and the second max, we can very easily predict how our sum will change. In particular, if we decrease our max by like 3, then, and maybe, so like this decreases by 3, and maybe there are like 5 different things, then our sum that are equal to the max, then our sum will decrease by 15. And that's a very predictable change. And as long as we're decreasing it by some number where there's only one unique type that's changing, this is a very easy thing to predict. So we don't actually have to go to our children in order to update our own sum. We can just mark some lazy propagation value, and then later on, if we need to look at our children separately, we can propagate that first, in the same way we would do lazy propagation for like range addition, for example. So we can do that, and when we do that, we can maintain what this sum is, and we can also break early a lot of the time. Now, what I'm saying here is a lot of the time, in the same way that we were just visiting our kids later on, or in the earlier problem. So for example, this range might cover this entire node, but we're still going to visit its 2 children. And this node, both of its children are the same, so it only has 1 max. So we'll be able to break out here. We don't have to visit its children. But this node, we might visit all of its children again. And when we do that, we visited a whole bunch of children. So now how do we convince ourselves that we won't be able to do this a bunch of times? And this is where the proof of the runtime comes in. It's a bit more complicated than understanding how to implement it, but I think it's still a very useful thing to know. So in order to prove this runtime, if all we're doing is like rangeMinWith, rangeSum, and we can even add rangeSet. So we want to set an entire range to some value. for these three queries, the proof is actually quite easy. So here's the idea behind the proof. Let's consider how many unique values there are in the segment tree. So initially there are order n values. So initially there are like n unique values in the entire segment tree. And then every time we do one of these rangeMinWiths, what we'll do is we'll visit some path on the segment tree. Maybe we visit this path here for the left kid, and maybe we visit this path here for the right kid. So this will be log n nodes. And that's fine. Every time we do a query, if we just visit log n nodes, then our runtime is going to be n log n. So we're not too worried about that. The thing that we need to be concerned about is visiting all of these nodes in the middle. And the important thing to keep in mind is we only are going to visit this node. We only look at all of its children if we're below the second maximum. So if we're between the maximum and the second maximum, or even if we're above the maximum, we can break out early. But if the maximum and second maximum get combined, for example in this node, then what that means is that those two values get turned into the same value. So for example, let's give some real numbers here. Maybe this was a 5 and this was a 7. And then we want to set each number in this range to the min of itself and 4. That's a good example. So we'll visit this left red arrow, we'll visit the right red arrow, but then when we get here, we see that our max is 7 and our second max is 5. And we see that 4 is less than or equal to 5. So this is like we're looking at this part, which means there's more than one unique value that gets changed. After we're done, both of these will be equal to 4. So we're setting all of these things to be equal to the same value. And when we do that, although we've gone down more paths, because we went down this extra path, then we've paid for it by deleting one element in the array. And we can only delete an element, like only delete a unique value log n times. So we have like n log n. This is for our normal queries. And we also have like log times the unique value, or unique values. And then this might be distributed across different queries in like non-obvious ways, but we can convince ourselves that this won't happen that many times in total. Why not? Well, initially we only have order n, and each time we rangeMinWith, we don't ever increase the number of unique values. Well, that's not true. Maybe we increase the number of unique values by up to like 1. We might create one new value. There might be two values that are the same, and we change one of them to a different value. So we might create a unique value here. And when we do rangeSet2, we also create at most one unique value. So every time we do a query, we increase this by 1. So we increase our total cost by log. And we have n log n normal queries. So in total, our runtime is just n log n. All right, very cool. So now there's one more thing that we need to look at that's described in this paper. One more type of query you can answer, and that's just this rangeAdd. Let's put it over here. So when you support rangeAdd, just like a normal segment tree, you just have like some lazy propagation value and you propagate it when you need to. But the thing to keep in mind is if you have this rangeAdd method, although it still works, the segment tree beats still work, and they're still pretty fast, it totally breaks this proof. So we now no longer have a proof of why it would be anything faster than n squared. Now, why does it break this proof? Well, when you do a rangeAdd, you can create a whole bunch of new unique values that weren't there before. So what if your array looked like this? It was 1, 2, 3, 4, 1, 2, 3, 4. This is the example they talk about in the comments of the paper. If you take this range here and you add to it, maybe you add like 4 to it, then you have 5, 6, 7, 8. 1, 2, 3, 4. So we've just created order n new elements. We've created n over 2 new elements in a single query. And if we can do that, then like we're in trouble, because initially we were under the assumption that every time we did a query, we created at most order 1 unique new elements. Now we've created a whole bunch all at once. The thing to keep in mind, though, is we've changed the number of unique elements by a lot, but we haven't changed the structure of the array by a lot. So if we can come up with some way of defining how this array is similar to itself, that isn't just the number of unique elements, then we can prove that it's actually still a pretty good runtime. So it turns out the runtime that we're looking for is going to be n times log n. That's our goal. Or n log squared, rather. When you have rangeAdd. If you don't have rangeAdd, it's just n log n. If you do have it, it's n log squared. So here's the here's like the reason that this works. We don't, like, when we're looking at the total number of unique elements, we're considering pairs of elements that are very far apart. So we value this 5 and this 4 being different, the same as we value the 5 and the 6 being different. But the 5 and the 6 being different can be changed in a lot of ways. So before we had these 1 and the 2, and these were different. But the fact that these two were the same, the 1 didn't count as a unique value. In reality, you have lots of pairs of elements that are very close together. And all of these elements that are close together are the same, or are different, but we're not counting any of that toward our potential, is what they call it. So the amount of like how different the array is from itself. And when elements close together are the same, then it's in some sense more important. So how do we handle this? Well, in the editorial they use these things called tags, and it's kind of understandable. I think a better way to explain it might be to look at it in a slightly different way. So what we're going to consider is we want to know what elements have two different maximums and it's two different children. So we'll say something is tagged if when you go left, the maximum of your left kid is different from the maximum of your right kid. So I'll draw maybe like a red X for all of the tagged ones. So maybe we start with all of these things. Well, I guess none of the leads will be tagged, right? So maybe all of these nodes are tagged. Initially, we have quite a few tagged nodes. And we can have at most order n tagged nodes in the beginning. So now what we're going to do is we're going to keep track of the number of tagged nodes. And the thing is, whenever we, like, here's the important observation. So if we have some range that we're querying, maybe we're querying this range here. Again, we'll have some path like this down to the left node. And all of these nodes will hit just in a normal segment tree query. And same thing, we'll have this other path down to the right node. We'll hit all of those nodes as well. Now the annoying part is for these nodes in the middle. How do we handle those? What we're going to do is we're just going to let our code run normally and see what would happen. So we have a bunch of these additional paths that we'll get. We might minimize the answer with a bunch of nodes here. We might run down like some path here. We might run down some path here. We might run down some path at this level, etc. So we'll have a bunch of these yellow paths that go down. And we're not going to worry about those because the green path can split off and at most log n different places. Because it visits log n different nodes, it can only split off once at each place. So we're not going to concern ourselves with the splitting off from the green path, because then we'll have a total of n log squared different yellow paths. Because we can split off once at each layer, and so we have log n different yellow paths. Each yellow path visits log n nodes, so we're n log squared there, so we're okay for the moment. Now the real problem will be when we have one of these yellow paths. A yellow path might itself split off again. And the second split off is what will really cause the problem, because if yellow paths can each split off, then this is an exponential increase in the number of nodes we can hit, and we might hit order n different nodes in a single query. And that would be a problem, because then our query would be linear. So it turns out that every time you split off, every time you have some yellow path, and this yellow path goes down, the yellow path will continue going down until it visits some node where it's max and its second max, where it's like smaller than the second max. So if it's smaller than the second max, what that means is the two will be merged. And all of the places these yellow nodes will stop at will be like one below a place where it destroys an x. So let's look at this yellow path here. If it went down to these two kids and it didn't stop early, what that means is it's smaller than the second maximum of this node. And since it's split off, that means it destroys this x here. So we can pay for the split by destroying the x. And every time we split off one of these yellow paths, we'll pay for an x similarly. So now if we also go down this path here, maybe we create some yellow path that looks like this. And maybe this splits off here as well. So this split, the only reason it can continue going through this node is because it's smaller than the second max. So we can pay for that x here. And similarly, it split off at this node. Or I guess it didn't split off at this node, so it wouldn't split here. Like what I drew would actually look like this. This split is because it's smaller than its second max. So that's how we pay for this. So now, like, why is this important? Well, once we've removed any x's, we won't be able to split anymore. And basically, if the maximum of your two kids are both the same, then if you go to both kids, that means later on, if the two maximums are the same, let's look at this. So maybe the max here is like 3, the second max is 1, the max here is 3, the second max is 2. So you're at this node here, and your path goes to both of your kids. That means you need to combine this 3 and this 2, because you're going to be smaller than 2 if you're smaller than the second max, which is 2. So you'll pay for some x that's in this node later on, and that x will pay for your split. And then if you wind up splitting down here, you pay for the x in a similar way. So that's basically how you pay for these marked nodes. And in addition to your n-log squared, which is going to be the green path and all the splits from the green path, those are all okay. Every additional thing that you pay for will be, or every additional split that you make will be paid for by some x. All right, very good. Now, we just have to show that the number of x's won't increase in any way that's bigger than like log per query. So an x represents when your two kids are different. Let's, yeah, okay. So we'll get rid of these. So now, how do we create an x? We can create an x with like a range set or a range min. When we do a range min, we'll change a couple nodes. So if we do some range min, maybe we range min with like this range here. Then the nodes that might create an x would be all of the nodes that split this range. So all of these would, because this border splits them. Similarly, all of these would. We're not going to create any new x's inside this middle part. If anything, we might just destroy x's. We might set two different maxes to be the same, but we won't create any more for sure. Similarly with rangeAdd, if we do a rangeAdd, shouldn't do x, I should use maybe we like plus a. If we add a constant to the whole range, then all of these nodes are changed in the same predictable way. So the max and the second max will both have the same value added to them. And if the max and the second max are the same, then that's added to both of them as well, and you don't create anything new. The only place this might create something is, again, on these split points, where it splits some node in half. And in all of these places, I guess these are really the same node, so it doesn't need two x's, but in all of these places, we might change one of the maxes and not the other copy of that same max. So we might create a second max by doing that. Or create a max for one of its children that's different from the other child. Cool. So that should be some good intuition for why these work in n-log squared, if you have rangeAdd. All right, there's one other pretty interesting thing that segment tree beats can store, and that's going to be the historic maximums. So this is also talked about in the paper, but basically what historic maximums are we have some array here, and we're going to do a bunch of operations on the array, just like with normal segment tree beats. Maybe we do some range adds, maybe we do some range minwiths, and at the end, what we want to know, or maybe in the middle even, what we want to know is what's the biggest that each element ever was. So formally, like, what's the max each position was. And this might seem like a pretty easy thing to do. It might just seem like at each leaf node, every time we change something, we keep track of what it is now or what it used to be, and we take the bigger of those two things and store that in some array, and that's our maximums. The issue is that doesn't work. There's a pretty big problem, and that problem is caused by lazy propagation. So what we know is if we have some node that's responsible for this range here, and we do some range add to it, maybe we add 5. Then after that, if we subtract 5, we need to combine those two propagations so that when we go to our kids, we only push down one event. We only push down one range add. And when we combine these two, it'll be a +0. Now the issue with this is that for this particular element, we're told there was just like a +0 operation. In reality, there was a +5 and then a -5. So we've lost the information that it at one point was 5 higher than it is now. And we're doing rangeMinWith stuff too, so there might be a bunch of other information that we could lose as well. So that's why this historic maximum stuff might be pretty difficult. You can still handle it, and you can still handle it in log squared time, even with this rangeAdd query. So let's talk about how you can do that. The main idea is instead of storing a value at each position in the array, what we're going to store is we're going to store a function at each position in the array. So I'm going to draw this graph here, and this will be the picture of what the function looks like. In this case, instead of doing rangeMinWith, we're going to do rangeMaxWith, and it's the same thing. It's just it makes the pictures a little bit easier to draw, and they also match the pictures in the paper, the blog post. So this will be the x-coordinate will be the initial value or the original value, and the y-coordinate will be the final value after you've done all of these operations. And we have one of these functions for every single position in the entire array. So the shape of this is going to look like, initially it'll just be some line. So the original value will be equal to the final value at each position. So if the original value is 4, the final value is also 4. But now we might do some operations. So the first type of operation we might do is we might max it with a given value. And if we max it with a given value, we have something that looks like this. So if the original value is very small, the final value will be equal to whatever we maxed it with. If the original value is big, it's just going to be equal to the original value. We might also add or subtract some constant. So maybe we subtract some constant, it looks like this. So now if the original value is really big, it's the original value minus, maybe we subtract 4. So it's the original value minus 4. Otherwise, it's going to be equal to maybe just 7 otherwise, if the original value was less than or equal to 11 or something. So we're always going to have some function that looks like this. And if you continue doing these maxWith, like you continue chopping off the bottom, and you continue sliding this up and down, the only thing you'll get is some function that looks like this. It's going to have this shape. It's going to have a straight horizontal line and then a line with a slope of 1. So we can do this and we can maintain it. It's pretty clear from this position what maintaining it would look like. If we chop off the bottom, you get some function that looks like this. If you add, you get some function that looks like this. So we can see that it stays the same. And mathematically, it's pretty clear what it would be as well. We're going to keep track of this for each node in the entire segment tree. So we're going to keep track of this value that needs to be propagated, and the value to be propagated is really a function. So yeah, so maybe, well, I guess it's not entirely a function. So for the leaf values, the final value is going to be a function. But for all of these other things, what it'll store is it'll store the yeah, I guess some function is fine. So it'll store some function that represents what needs to be propagated. So by default, they'll all just be some line with a slope of 1 that goes through the origin. But then maybe in this node we say, okay, we want to add 5 to each node. So if we add 5 to each position, we'll get something that looks like this. We'll get that line, and we'll slide it all up. And maybe we also want to max it with some value, so we'll get something that looks like this. So now when we apply this function to this other value, what that is it's a series of two things. So first we do an addition, and then we do some max. And that's, since all this function is it's some addition and some max, we can apply an addition and a max to some other addition and a max, and we'll get some other constant. And it's pretty clear why that's true. So like we can get this function is just represented by this line slid up and then have the bottom chopped off. So what we can do is we can do the same thing to this blue line. So if we want to slide it up by some amount, maybe we slide it up to here, and now maybe we chop the bottom off here, or maybe we chop the bottom off here and it doesn't do anything. So that's how we can propagate this function down to its kids. But we still need this historical maximums, and it turns out that the historical maximums are also, we can make some function for them, and that also propagates really nicely. It stays in the same type of graph. So if we have two graphs like this, and we want to take the maximum of the two graphs, in this case it'll look like this. So the maximum of the white and the red in this picture will be the blue. And yeah, this is pretty neat, because what this shows is, like, visually, it shows that the maximum of these two functions is a function that's of the same type. Let's do some math by hand to see what that would look like. So what this function is going to be is it's going to be the max. Let's say this is going to be f of x. So f of x is the result of doing all of these operations, so whatever we started with, and what we started with we'll call x. So this is going to be equal to the max of x plus some a, and a is like the amount we slid up, the max of this, and b. So we can apply these operations really easily. Let's see what it looks like when we want to take the max of two different ones of these. So now we have this g of x, and g of x is equal to, we take whatever our kid was and we apply some functions to that. So now this is going to be equal to the max of whatever our kid was, that's f of x, plus some new constant that we're storing in this g function. Maybe that's going to be c, and the max of this, and d, I guess we'll say. So what we can do is we can take this g function, we can expand it out, or we can expand the f function inside the g. So this is going to be equal to the max of x, of the max of x plus a, comma b, and this amount, plus c, and d. Alright, so what I did there is I just took this f and I replaced it with the value for f. So what we can notice here is if we're taking the max of these two numbers and then we're adding a constant, what this really is this is going to be just the max of x plus a plus c, because we can add this c in here, or b plus c, or d. So we're just taking the max of three numbers here. What you can notice is these two are just a constant. Like, this is just some constant. So what this is equal to is now we have the max of x plus a plus c, and some constant, I guess we'll call it e here. And now e is just going to be whichever one of these two is bigger. So if we want to figure out like what this will be when we propagate it, it's simply equal to this new value. And yeah, I guess that's that kind of demonstrates that when you do this propagation, you maintain something of the same form. Like both what we started with, which is x plus a constant maxed with some constant, and what we have here, which is x plus, this is just a constant here. Like this value here, a plus c, is just equal to some constant, so x plus some constant maxed with some other constant is what we ended with, which is of the same form. So we can very easily maintain graphs that look like this just by storing them in this compressed way. That'll give us how to transform these when we do our lazy propagation. We also want to keep track of this maximum here. And I won't go through the math for that because I think it's a bit tedious, but it's very similar in the operations. You do the same distribution and it winds up of the same form. And you can see that from the picture. That should be some proof that that's true. I don't think the historical maximums are too useful in practice. I haven't ever seen them come up. But I also didn't look through all the problems in the paper, so it's possible that they do as well. Yeah, okay, so we can maintain all of that. Now, this there's one last thing I'd like to mention about this, and what that is that since we're keeping track of this function here, we're keeping track of two functions really. We're keeping track of well, erasing that wasn't helpful, I guess. Yeah, so we keep track of two functions in each node. One, we keep track of the current value, like the current function for the current transformation. We also want to keep track of the maximum value for the maximum transformation. And also like the max value. So if we keep track of these two things for each position, what we can do is not only can we answer all of these queries, but we can also answer this additional query, which was pretend the initial value, like pretend a at I started at x, instead of whatever it did start at. And instead of having to go redo all of these queries for this particular index, now we can just say, oh yeah, so now whenever we evaluate it, instead of evaluating it at this position, we'll evaluate it at this position. We don't have to change anything in our segment tree, we just have to change when we evaluate it what it will be. Actually, I guess that's not entirely true, because if we're doing segment tree sum, like rangeSum, then we have to update that particular node. But still, it's fairly reasonable on how we could do that. We just need to maintain more stuff in our nodes as well. So that's all I have for segment tree beats. It's a pretty powerful topic. There's a lot of stuff you can do with it, and I hope you enjoyed it. If you have any questions about it, feel free to post them in the Codeforces blog that I'll post in the description. Ericto on his second channel has a pretty good video on this, so I recommend watching that if you are still confused. And also there's definitely the paper that I've mentioned several times, and I'll post both of those in the description as well. Yeah, have a good day, and the next video will be on persistent segment trees, and you can do a lot of really cool stuff with that, stuff that shouldn't seem possible or seems like it would be n log squared at the very least, but a lot of times it winds up just being n log n. It's some very powerful queries. Goodbye.